I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to start the second module in engineering physics, that is Introduction to Solids and Semiconductors. In that Introduction to Solids and Semiconductors, we are going to discuss in detail about the free electron theory. So what I would like to tell you about this theory is, whatever we are going to discuss today is all the developments, how the developments took place in the free electron theory, which led to the band theory of solids, which is an established one. I can say that this will be the foundation for you to understand semiconductors. So hope you will note down every point in detail. So coming to the free electron theory, this is the electron theory of solids, which aims to explain the structure and the properties of solids through their electronic structure. So whatever metals or non-metals that are found in nature, if scientists have to understand their electronic structure, their properties, first they have to study the electronic structure. And in order to study the electronic structure, they need to understand this free electron theory. And by studying this electronic structure, what they can explain is the electrical, thermal, as well as magnetic properties of solids. Unless you know about their electrical properties, if I speak about electrical properties, how they conduct, whether they are able to conduct the electricity through them or not. So they are the electrical properties. Then thermal. Thermal is always related to heat. How do they conduct heat? And then comes the magnetic properties of solids. So now the establishment of free electron theory with the help of electronic structure helps us to explain the electrical, thermal as well as magnetic properties of solids. Therefore, understanding this theory is very important. So let us see how this theory is developed. It is developed in 3 stages. Okay, what are the 3 stages? The classical free electron theory, which we call it as CFET. CFET stands for classical free electron theory. Okay, this theory is completely based on classical concepts. In our previous lectures, we have seen in detail about the classical mechanics. What were the problems with the classical mechanics? How it could not explain some of the phenomena that occurred in nature. And then the development of quantum free theory or quantum mechanics, which could solve many problems that were not unexplainable by classical mechanics. Then comes the quantum free theory. Quantum free theory, we are representing it by QFET. Q stands for quantum free electron theory. So whatever that could not be explained by classical free electron theory, most of the things could be explained by quantum free electron theory. And then still there were certain things which were unexplainable with the help of quantum theory, and that could be explained with the help of zone theory, and which we now call it as band theory of solids. So what we are going to discuss today is these 3 theories in detail. Now first we will start with classical free electron theory. This theory was proposed to account for the electrical conduction. So mainly they want to explain the electrical conduction in metals. If you have a metal, so how does it conduct? If it is acting as a good conductor, so how it acts? What are the things that are helping in conduction in metals? This was done by the scientist in the year 1900. And then there is another scientist by name H.A. Lawrence. He extended the Drude's theory in the year 1909. And this theory, we simply call it as a free electron theory also, free electron theory of metals. Actually, because it is based on the classical concepts, we call it as classical free electron theory, or you may simply say it as free electron theory. So what does this free electron theory talk about? Metal atoms have one or more loosely bound electrons. So whenever you take an atom, if I am talking about a solid, whether it is a metal or a non-metal, it consists of a number of atoms. Now we are talking about a metal which consists of a number of atoms. And in an atom, what we have is a nucleus and electrons revolving round the nucleus in fixed orbit. And depending upon the atomic number of the solid or the element we are talking about, we have the number of electrons. Now, what they are telling is every metal will have one or more loosely bound electrons. What do you mean by loosely bound? Loosely bound here means they are not bound to the nucleus or to the atom. They can be made free very easily. So that is what we mean by loosely bound. They are not strongly attached to the atom. So such electrons get detached easily, even with small thermal energy. Thermal energy means, I told you, thermal is always related to heat. So when you supply a little amount of energy, thermal energy means when you heat it, for that matter they said even at room temperatures. The temperature, room temperature may be around 25 to 26 degrees Celsius also you take, what happens? These electrons get detached easily. And these electrons which are detached from the atom, they are neither shared nor acquired by any of the atoms of the metal. So once the electrons are detached from the atom, they are moving freely. They are neither shared with the other atoms nor acquired by the other atoms. So they are free and they make a common pool. Here we are talking about a common pool of electrons. The electrons which are free now. So I'll mention common pool of free electrons. So those electrons which are loosely bound, when you supply the energy, they are detached. And after detachment, they are neither acquired nor shared by the other atoms. So they are absolutely free. So when they are free, they form a common pool of free electrons. Now these free electrons, what they do? They represent a metallic solid as a container filled with gas composed of free electrons. So because they are free, what we are talking about is if you are taking a container and if this container is filled with gas. So all the gas molecules which are present inside can move very freely inside the gas. Now what they said is according to the free electron theory, because the detached electrons are absolutely free and they are moving freely, you can represent them like a container which is filled with gas. So what we need to understand here is, just like the gas molecules move inside a container very freely, these electrons also move very freely inside the metal or inside the solid. So, and they said these electrons are responsible for electrical and thermal conductivity because they are trying to explain mainly the electrical conduction. So they said these electrons which are free are responsible for electrical as well as thermal conductivity. Now these free electrons are considered identical to the outermost or valence electrons of a free metal. Now if you understand, after this theory developed, then after the quantum mechanics, we had that electrons cannot have continuous energy. They have to be in discrete levels. Then the concept of valence electrons has come up. So they are assumed to be moving independently of one another throughout the entire crystal. If you talk about the free electrons, they are absolutely free and they can move freely through the entire crystal like it is resembling electrons which are put inside a container which can move very freely just like the gas molecules. Now, when we have considered these free electrons, the electrostatic interaction of the detached electrons with the positive ion cores and with other electrons is assumed to be negligible. Actually, this is becomes a drawback of the free electron theory. Now, if you are considering a solid, or I will consider an atom, in an atom you have a number of positive and negative ions. Now, when the electrons are detached, I will represent them like this. Suppose you talk about a crystal lattice or a solid. The electrons that are detached are shown. These are electrons. Okay. So, what they are talking about here is the electrostatic interaction of the detached electrons with the positive ion cores and also with the other electrons is assumed to be negligible, because in the previous slide we have seen these electrons can be made very easily free, very easily, because they are loosely bound, and when they are made free they can move very freely inside the crystal. Now if you see this picture, when these electrons are moving, they may collide with the positive ion cores or they may collide with other electrons also, but they said that it is assumed to be very negligible. Okay, they have not considered the collision of these electrons with, or the interaction of these electrons with the positive ion cores or with the other electrons. Then when an electric field is applied, the free electrons will experience slow drift motion in the positive direction of the field and produce a current. And because they have to account for the current, how is the current flowing? Then they said if you are taking a metal plate or a solid and you apply an electric field. Now these electrons, you are considering it as a pool of electrons. These electrons, what happens? They will drift towards. Drift means shifting towards. Drift in the positive direction. This is the positive plate, and with the help of this we are applying an electric field. So when an electric field is applied, the free electrons will experience slow drift motion in the positive direction because of the opposite charges. These electrons considered to be negatively charged, so they will drift towards the positive. When they are drifting, the motion of these electrons will produce the current in the metal. This is the explanation that was given by free electron theory. Now, what are the assumptions that were made in classical free electron theory? So, in metals, there are a large number of free electrons, because if you consider any solid, it consists of large number of atoms. So, even if one or two electrons are made free from each atom, there will be large number of free electrons and they move freely within the metal. That is what we have seen. And the electrons revolve around the nucleus in an atom. This is the first point. They are free electrons and they are moving around the nucleus. Now, these free electrons are assumed to behave like gas molecules. This point also we have discussed. They are free to move in any direction and the collisions are also assumed to be negligible. So, they are compared with the gas molecules that obey the kinetic theory of gases. So, we all know the kinetic theory of gases. In kinetic theory, what we talk about is When these gases move, the molecules inside the container move very freely. They move in random direction, maybe because of the collisions with the walls or against the other molecules that gives rise to the pressure and volume. Okay, so now they started explaining that these electrons which are moving like gas molecules, they obey the laws of kinetic theory of gases. And the mean kinetic energy of each electron, because now the electrons are moving, they definitely possess kinetic energy. And the mean kinetic energy of the free electron is equal to the gas molecules, to the kinetic energy of the gas molecules at that temperature. So even if you are talking about gases, as the temperature increases, the kinetic energy of the molecules increases. Here what they said, as the temperature increases, we can make the electrons free. And these electrons are free to move anywhere inside the metal. And the energy, the kinetic energy of the free electron is equal to that of the gas molecule and at that same temperature. Now, electrical conduction is due to the motion of free electrons only. So now what they are talking about is only about the electrons that are detached from the metal, and the positive ion cores are at fixed position. The positive ion cores are at the fixed position. The free electrons undergo incessant collisions with the ion core. That is what they have considered. The electrons are free, but the positive ion cores are not moving. They are at their fixed position. Later on, it proved to be wrong. That is what development we all know. What we are trying to understand now is what was it before the theory we understand now. How did it develop? So what was considered is only the electrons are moving and the positive ion cores are in their fixed position. And the electric field due to the ion cores is constant throughout the metal. That means the free electrons move in a completely uniform potential field due to the fixed positive ion cores in the lattice, and the repulsion between the electrons is negligible. So one more thing comes here, because they have not considered the collision of the electrons with the positive ion cores or with the electrons. They have not considered. They assumed that it is very negligible. So what they are telling here is the free electrons are moving in a completely uniform potential field. So in free electron theory, what we consider is a uniform potential field throughout the lattice, and the repulsion between the electrons is negligible. Now when an electric field is applied, what happens? The free electrons are accelerated in the direction opposite to the direction of the electric field. This is what we have seen. Because the electrons are free, once you apply an electric field, these electrons will move in the opposite direction, that is towards the positive plate. Now what about the electrical conductivity, the drift velocity and the mean free path? So in metals, free electrons move freely throughout the lattice because they are free. We said they drift towards, no, because of the applied field, they drift. Now, in between two collisions, the electrons will move with uniform velocity. Now, when they are colliding with each other, after collision, between one collision and the other, they will have to move a certain distance, even though it is very small. So, they are considered to travel with uniform velocity. And during every collision, both direction and magnitude of the velocity will change, because now these electrons are moving with uniform velocity. But what they have considered is, after collision, their directions may change and the magnitude of the velocity may change. But in between, the velocity remains constant. In the absence of the field, the electrons may have random motion just as the gas molecules in a container. So this is what we have seen. The velocity that is acquired by the electrons is due to the applied field. What happens when there is no field? When there is no field, these electrons had random motion. Random means they move in any direction they like, in any random direction we say. So just like the gas molecules in a container. So these randomly moving electrons undergo scattering and they change the direction. Scattering means once they collide with the other particles, they scatter away. So, and then they change the direction. And this random motion contributes to zero current. And this velocity, we call it as random velocity. Because the motion is in random direction, they may move in any direction. So these electrons are not moving in a particular direction. So it does not give rise to current. They may cancel out. Okay. And then the random motion contributes to zero current. Means what we can conclude here is only in the presence of applied field we see the current, and when there is no field the current is zero. In the presence of a field, in addition to random velocity, there is an additional net velocity associated with the electrons, which we call it as drift velocity. So we have seen those electrons which are moving in random directions and they are having random velocity. On application of electric field, they are able to get one more velocity which we call as the drift velocity. And this drift velocity is due to the applied field. How do we represent the drift velocity? By Vd. V suffix d always represents the drift velocity of the electrons. And the drift velocity is always due to the applied field. Okay, how do these electrons drift? These electrons which possess negative charge, they move opposite to the field direction. So we have seen what do we mean by opposite. Positive, negative, I say this is a container or the solid. All the electrons which are there here, they will drift towards the positive slowly. Now they are no more moving in random direction. Okay. Once we apply the field, all their motion, because they are negative, they are drifting towards the positive. Now, if n is the number of conduction electrons per unit volume, then the charge per unit volume is minus NE. So, what we are trying to find is what is the charge that is developed because of the electrons. It depends upon the number of electrons per unit volume. So, here we can write the Q is equal to minus NE. E here is the charge of the electron. N is the number of electrons. We are showing minus because they are electrons. So, we have established that the charge is per unit volume is given by minus N. And the amount of charge that is crossing per unit area, per unit time is given by current density. So, we are now slowly coming to establish how do we calculate the charge depending upon the number of electrons, and how do you calculate the current density. What do you mean by current density? Current density J is equal to the amount of charge crossing unit area per unit time. So this gives us the current density, the amount of charge crossing a unit area per unit time is given by current density, because we said the movement of electrons gives rise to the current, produces current. And how do you calculate the current, or the current density is given by the number of amount of charge per unit area per unit time. Now coming to Ohm's law. Ohm's law governs the electrical conduction in metals. So this classical free theory was successful in explaining the Ohm's law. What does Ohm's law say? As long as the physical state of a conductor remains the same at constant temperature, the current flowing through the wire is directly proportional to the applied potential difference. If there is a difference in potential that is applied between the two ends of the wire, and as long as the physical states, that is the length, the area of cross section, all these remain constant, and we are doing it at a particular temperature, I should be proportional to V. V here is the applied potential. Because of the applied field or the variation in potential, you are having the movement of electrons, and these movement of electrons produces current. So I is proportional to V. The current is due to the motion of the conduction electrons under the influence of the field. So how are we getting the current? Due to the motion of the electrons. And this motion is under the influence of the electric field. Now the field exerts a force of minus EE on the electrons. What is the force that is exerted on these electrons? Due to the applied field is given by minus E into E. So these electrons are experiencing a force given by minus E into E. E is again the charge and capital E is the electric field. Now, due to the application of electric field, electrons are accelerated. Accelerated here means they start moving fast. So, what are the success of classical free electron theory? Where did it become successful? So, it proved the validity of Ohm's law. That is what we have seen now. I is proportional to V. So, it proved the validity. It could give a satisfactory explanation to the mechanism of electric current in conductors and thermal conductivity in metals. When we are talking about conductors means which can conduct the current very easily. So how is the current flowing in conductors? That could be well explained with the help of free electron theory. And also thermal conductivity, how heat flows through metals. Metals are good conductors of heat, we say. So the thermal conductivity of metals also could be easily explained with the help of free electron theory. It explains the optical properties of metal. Optical properties means with related to light. So how do they reflect? How do they transmit? And all the other optical properties are very well explained with the help of free electron theory. It also derives the Wiedemann-Frenz law. This is the name of the scientist who gave a law. What this law talks about is the relationship between electrical conductivity and thermal conductivity. Means if a metal is thermally conductive, means it is active. Now thermal conductivity means if its thermal conductivity is good, its capacity to conduct the heat is good. What about its electrical conductivity? So that relationship was given by this scientist Wiedemann-Frenz. So this could also successfully explain the Wiedemann-Frenz law, which connects both the electrical conductivity and thermal conductivity. Now coming to the failures. Where did it fail? Classical free electron theory. It could not explain the temperature dependence of resistivity of metals. If the temperature varies, how does the resistivity vary in metals? This free electron theory could not explain. And also the heat capacity and paramagnetic susceptibility. Because when we were talking about the electrical conduction and also the thermal properties as well as magnetic properties. Paramagnetic susceptibility. Susceptibility talks about the property of the substance to allow the magnetic lines of force to pass through, how much susceptible they are. Okay, that could not be explained with the help of this theory. And also, it could not predict the correct values to the mean free path of the electrons. What is mean free path? We said in between the collisions, these electrons move. They move with uniform velocities. And what is the path, the mean path or the average path that is traveled by the electrons? They could not predict the correct values with the help of this free theory. So these are the failures of classical free electron theory. Now to overcome the drawbacks of classical free electron theory, a scientist by name Sommerfeld, he developed a theory in 1928. What he considered the Drude's assumption of free electrons. What did Drew would consider? Any atom you take, it consists of some free electrons, and these electrons are free. They can be made free very easily just by supplying a little thermal energy. And then he applied the Pauli's exclusion principle. Pauli's exclusion principle is also very important in developing the quantum free electron theory. So he took the assumptions of Drude regarding free electrons, and then he applied the Pauli's exclusion principle. What does Pauli's exclusion principle say? Is no two electrons can have the same quantum number. No, it has to be different. And then he also applied the Fermi-Dirac statistics. What is Fermi-Dirac statistics? It talks about the energy of the electron. Okay. So in Fermi-Dirac statistics, what do we talk about? The F of E. The energy is equal to 1 upon e power E minus EF upon KT. Okay. So this is the Fermi-Dirac statistics. In Fermi-Dirac statistics, we consider that they are identical, but their spin is different. Fermi-Dirac considered the Pauli's exclusion principle. No two electrons can have the same quantum number. So at least their spin has to be different. So he started talking about half integral spin of these electrons, and which was not there in Maxwell's Boltzmann constant, in this Maxwell-Boltzmann statistics. He considered that all electrons, there is no restriction for the electrons, they can be in any quantum state. That was the assumption taken by Maxwell-Boltzmann. This was used in classical theory. So they made use of the Pauli's exclusion principle, and they applied the Fermi-Dirac statistics instead of Boltzmann statistics. Then what happens? The results of these modifications indicated that not all free electrons would contribute to the process of electrical and thermal conductivities of metals. So when we were talking in the classical theory, we said all free electrons, they form a common pool, and when you apply a magnetic electric field, they will drift, and the drift velocity or the movement of these electrons is responsible for current. But these are the people who first said, because they have brought theory which included the Pauli's exclusion principle also and the Fermi-Dirac statistics also, which resulted in understanding that not all free electrons would contribute. So we cannot consider all the electrons that are present in the atom to be responsible for the conduction of current. So only a fraction, only a small fraction of the free electron gas would participate in such properties. Such properties means what we are talking about, the electrical as well as the thermal properties. So they brought a bifurcation among the free electrons also. Which electrons are responsible for conduction and which electrons do not participate in conduction. Now, according to the quantum free electron theory, a conduction electron in a metal experiences constant or zero potential and is free to move inside the crystal. But it will not come out of the metal because an infinite potential exists at the surface. Now they will have to answer why all electrons are not participating in the process of electrical conduction or thermal conduction. So for that, what they said, as long as you take a metal, there are free electrons. These electrons are free to move inside the crystal and in a region of constant potential, but they cannot come out of the metal. Only those electrons which can come out of the metal only will participate in conduction. That is what the quantum free electron theory says. And how these electrons will overcome the infinite potential that exists at the surface. When I am talking about the electrons cannot come out means there exists a potential, and this potential is infinite, huge. Only when the electrons can overcome that, they will be able to made free and they only can participate in conduction. That was the explanation given by quantum free electron theory. Now, what is the success of quantum free electron theory? It could explain the specific heat and the paramagnetic properties. So, if we have seen the free electron theory, they could not explain the specific heat. What is specific heat here? What is the amount of heat required to raise the temperature by unit of a given substance? It is a individual substance. It depends upon the material or the solid that we are taking. Then it could predict the temperature dependence of resistivity also. So, free electron theory could not explain the temperature dependence on resistivity. But with the help of quantum free electron theory, this temperature dependence on resistivity also could be explained. And they could also explain the thermionic emission of electrons from the metals. Means, how do you make the electrons come out of the metal? Thermionic emission. Emission means emitting of the electrons from the metal surface. Thermionic emission is by supplying heat. Heat is nothing but a form of energy. You have to supply energy to these electrons to overcome the barrier, that overcome the infinite potential at the surface. So, thermionic emission also could be successfully explained with the help of quantum free electron theory. Then why did it fail? Why did quantum free electron theory fail? They said if all electrons, all atoms have free electrons, all of them do not conduct, but some of them help in the process of conduction, only participate in conduction, then why some materials are good conductors? When I say good conductors means they conduct very easily. If I am talking about electrical conduction, they allow the current to pass through them very easily. So, some materials are good conductors, means they allow the current to pass through. Why some materials are insulators, good insulators? Why I am talking about good insulators is they do not allow the flow of current. Means there is no movement of electrons. Why are these differences occurring? Why some are behaving like good conductors and why some are good insulators? And also there are some materials which are semiconductors. Semiconductors means their conductivity lies in between conductors and insulators. So, quantum theory, quantum free electron theory could not explain this classification. Okay, so in total it failed to explain the classification of materials based on conductivity. This is the classification we see based on conductivity. Those whose conductivity is very high, if the conductivity is very high, we say they are good conductors. If the conductivity is very low, we call them as insulators. And if it is in between, you call them as semiconductors. But the quantum free electron theory cannot explain this classification of materials. Okay, so what did we see after the quantum free electron theory? Now, before moving on to the next theory, we will just try to compare between the classical free electron theory and the quantum free electron theory so that the concept will be very clear for you. In classical free electron theory, there are a large number of electrons moving freely and they behave like gas molecules obeying the kinetic theory of gases. This is what we have discussed. Then in quantum theory, how did we see the electrons? The electrons are fully responsible for electrical conduction and they move in a constant potential inside the metal. They cannot come out of the metal, but they move in a constant potential inside the metal. Now, in classical free electron theory, we see that the electrons move randomly, means in any direction, and they collide with either positive ions or with free electrons, and all collisions are elastic. And here, the electrons have wave nature. In the quantum theory, we have already established that electrons are exhibiting the wave nature and their velocity and energy distribution is as per the Fermi-Dirac distribution. Means he has considered the Pauli's exclusion principle also. So, in free electron theory, the Fermi-Dirac distribution function for the energy of electrons comes into picture. Then, when an electric field is applied, what is happening? The free electrons accelerate in the opposite direction to the applied field. The electrons are accelerating in the direction opposite to that of the applied field. And here what happens? The electrons are distributed in various energy levels according to Pauli's exclusion principle. So here they are talking about different energy levels, because quantum free electron theory always talks about the quantum nature of energy. It is not continuous, they say. Now the energy is different in different energy levels, and why it has to be different according to Pauli's exclusion principle. Now, what are the advantages and drawbacks of CFET? That is, first we will see the classical free electron theory, then we will see the quantum. So, it verifies the Ohm's law. Yes, the current is directly proportional to the velocity. Okay, but it fails to explain the temperature dependence of electrical conductivity. It could not explain the temperature dependence. Then, in the advantages, what we see, the electrical and thermal conductivities of metals could be explained. What they said, the free electrons are moving, so because of that there is current. And then it derives the Wiedemann-Frenz law, which is connecting the electrical conductivity as well as the thermal conductivity, and it also explains the optical properties. So all these are the advantages of classical free electron theory. Coming to the drawbacks, means the failures, what it could not explain. It could not explain the temperature dependence of electrical conductivity, and it does not account for the specific heat capacity of a solid. Now it could not explain the why the specific heat capacity of a solid is fixed for a given material, and it could also not explain the electrical conductivity for semiconductors and insulators. It is always talking about the conductors which will allow the current to pass. Then what about the semiconductors which are partially conducting and insulators which are not conducting? So these are the drawbacks of classical free electron theory. Now let us see the advantages and drawbacks of quantum free electron theory. So quantum free electron theory explains the specific heat capacity of materials. So where classical mechanics failed, quantum mechanics proved to be successful. It could explain, and it fails to explain the photoelectric effect, Compton effect and black body radiation. So these are according to quantum. No, but what classical mechanics could not explain. So classical mechanics failed to explain, but this has become an advantage for quantum mechanics or the quantum free electron theory. It derives the mathematical expression for thermal conductivity of metals. How it depends upon the temperature. That derivation also was given by free electron theory. Now the major drawback of QFET is it could not explain the classification of materials. The classification of materials into conductors, because we consider metals are very good conductors. So it could not explain this classification. Why some are behaving like conductors, some are semiconducting and some are very bad conductors. This free electron theory could not explain. Now the failure of quantum free electron theory to explain the classification of materials led to rethink the basic assumption. So they started thinking, why are we not able to explain the classification of materials? So then they started thinking, what was the assumption that was made? So what was the assumption that was made in quantum free electron theory? They considered that these electrons are moving in a constant potential inside the crystal. So they started questioning, is the potential inside the crystal really constant? That is what they wanted to understand. Because they failed, they started to look back and see what were the assumptions that were made and are the assumptions correct? Then later on it was realized that the oversimplified assumption that the potential in which the electrons move is zero or constant is not the actual picture. Okay, so what they considered is whenever you have a metal, you have the electrons moving, and as long as they are inside the metal or the solid, they move with constant, they are under constant potential, and only at the surface they'll have to overcome that infinite potential. That was the assumption made. So now they started thinking, so is the potential constant? Then they realized that the potential of the electrons is not zero or constant inside the metal. The potential must be varying. Now let us consider the picture of variation in the potential. So what did they consider here is, if you are considering about this lattice, positive ion cores, and you have electrons which are detached. Okay, so this is the picture, and we are only talking about the x-axis. No, we are not talking about the other things. Now, if we plot the potential energy of a conduction electron as a position in the lattice, the variation in potential energy is shown by this figure. So, what we are plotting? The position with respect to the potential. Now, they have understood that the potential is not constant inside the metal. So, we are coming up with a concept of varying potential. Okay, slowly the concept of varying potential inside the metal atom has come up, because when they have plotted, they saw that the potential is varying. Then they started trying to understand why the potential is not constant. Why the potential inside the crystal is not constant. So, to explain that, they have considered a crystalline solid which consists of a large number of ionic cores. So, these are the positive ion cores, and they are placed at regular intervals. Regular intervals means what? At equal distances from one another. If you see, they are equal, regularly spaced. Positive ion cores. And the conduction electrons move throughout. Now we have the electrons that are detached, move freely inside. And these electrons move in a periodic potential or between the positive ions. So they do not move in a constant potential. They are moving in a periodic potential. How is the potential varying? So the periodicity arises due to the periodic arrangement of positive ions. Now they are periodic in nature, I said, spaced in a regular arrangement. Now when an electron approaches a positive ion, now I have an electron here. This electron is moving from here to the positive ion or in any direction here. Then what happens? There will be an attraction between the two. This is negative, this is positive, because in the earlier theories, we did not consider, especially in the classical theory, we have not considered the attraction between the positive and the negative electrons. That was, they said it is negligible. But here they said, because the potential varies. How is the potential varying? Because of the force of attraction between the negatively charged electron and the positive ion core, the potential decreases. So where is the potential minimum? The potential is minimum at positive ion sites. So wherever there are positive ion sites, if you see, these are the positive ion sites, and this is the potential we are talking about. And in between, the potential may be maximum, but at the positive ion sites, you may see that this is the minimum it can have. So the concept of varying potential inside the crystal due to the presence of positive ions is introduced. So what was the main change, the radical change we are going to see is, before we were considering that the electrons were moving in constant potential inside the crystal, but now they are considered to be moving in varying potential. And this varying potential is due to the interaction or the attraction between the positive ion cores and the electrons. And because of this attraction, the potential reduces. So what we see is at every positive ion site, the potential energy is minimum and it increases in between the two positive ion sites. So there exists the concept of, arises the concept of varying potential, where the potential varies inside the crystal lattice also. Now the failure of free electron models, that is the classical and quantum, is due to the oversimplified assumption that the interaction between free or detached electrons and the positive ion cores is negligible. So once this is established, once they could plot, they could see that the potential is varying. So this oversimplified assumption was wrong. They could realize. In reality, what we see, the free electron ion core interaction cannot be neglected. You cannot neglect. So potential due to the positive ion cores cannot be taken to be constant throughout the crystal. These are the conclusions. So whatever the oversimplified assumption they made was wrong, and the interactions between the free electron and the positive ion cores cannot be neglected, and the potential due to the positive ion cores is uniform because they said they are fixed, they do not move. So therefore, there is constant potential in which the electrons are moving. That is also constant. So therefore, the detached electrons cannot be completely free. Why they cannot be completely free? We are talking about the interaction between the electrons which are detached and the positive ion cores. Now, how are we looking at this? If you consider a periodic potential due to the positive ions. So, these are the positive ions periodically spaced. Okay. And these are the electrons. Now, if you are considering an electron which is moving in this direction. So, where at which position will the energy, the potential be maximum and when will it be minimum? So, if an electron moves through these ions, it will experience varying potential. Definitely, an electron is starting from here and it is moving like this. Then what happens? The potential of the electron at the positive ion site is 0. So, here it may be minimum. Okay, until it comes to another positive site. In this region, the potential may be maximum. Here it may become minimum. And then again, this electron, until it comes in contact or in interaction with another positive, it may increase. But when it comes here again, it becomes minimum. So this is how it keeps on varying. Again, it will increase. Here it again becomes minimum. So if you see the movement of an electron inside the metal or in the crystal lattice where the positive ions are uniformly spaced, there is a varying potential and it is minimum at the positive ion sides and maximum in between two ions. So consider the potential experienced by this electron when it passes along a line through the positive ion cores. So when they have considered this potential variation, they said the oversimplified assumption was wrong and they are experiencing various potentials that can be utilized to explain the classification of materials. There comes the band theory. So while Sommerfeld theory accounts satisfactorily for electrical conductivity in most metals, but it failed to explain why other substances which also have free electrons virtually had no conductivity and they are considered to be insulators. This is what they could not explain. Sommerfeld made so many changes. He could explain many of the things, but he failed to explain the classification of materials. So virtually no conductivity means why some materials, because when every material has free electrons, they all should conduct. But why some materials are not conducting and they are behaving as insulators, this point he could not explain. And the solution to this problem is given by zone theory or band theory of solids. In the beginning of the lecture, I told you that we are going to see three stages. The first one is the classical free electron theory, and then the quantum free electron theory, and then the band theory. So whatever quantum theory could not explain, that is, the classification of materials, that problem could be solved very easily with the help of band theory of solids. So I conclude my lecture here. Thank you. See you in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.